So before we proceed to motion graphs, it's important to know also motion diagram. So as an introduction, let me share the screen. This is from the textbook, Randall Knight, the author of the physics book. So there are types of motion. Four basic types of motion. We have linear motion, circular motion, projectile motion, and rotational motion. For our purpose, let's start with linear motion. So how the motion diagram is made. So it's just like there's a video camera taking images at a fixed rate, like 30 every second. So you have there the picture of a car with a tree, and next picture, the next video taken with 30-second interval, it's already here in this position. So each separate image is called a frame, and then shown are four frames from a video of a car going past, and then the car is in somewhat different position in each frame. So what if the video is edited by layering the frames on top of each other, creating the composite image shown below? So that edited image is already a motion diagram showing an object's position at several equally spaced instants of time. So in this case, they have equal same amount of time elapses between each image and the next. And like, for example, this Lolo on a skateboard is having a constant speed because it is equally spaced. But for this girl, which is who is running, and then it keeps on increasing its separation distance, so this is speeding up. And this one, the separation distance becomes lesser, so it is slowing down. So that is how a motion diagram was created, by having that frame of images superimposed on each other and making it as a particle represented with the dot. So that's why we have the separation distance from 0 second to 1 second, 1 second to 2 seconds, and so on. So same amount of time elapses for each image, and you just take note of the separation distance to identify whether it's slowing down or speeding up. Okay, this is a rocket being launched from the ground. So take note, from 0 to 4 here, the separation distance keeps on increasing. So it's speeding up. Okay, so from the motion map or diagram to the motion graph. So if it's having a constant separation distance, if you plot it in the x versus time, so it will give you a straight line like this. And based on your math concept, a straight line like this will have a constant slope. So a slope is rise over run. Our rise here is position, the change in position over the change in time. So we'll give you the slope or the average velocity. So that is why we have now the delta x over delta t or delta y over delta t, because we can also have the motion along the vertical, so delta y. So we can place also the y here in the y-axis, or x in the y-axis, because it is the position. And here, signs of velocity and acceleration as a review: if same sign or same direction, it speeds up. Okay, so faster result. So like, for example, same sign also, it's faster in the negative x direction. If it's opposite sign, velocity and acceleration, it is slowing down in that direction. Okay, so that is for the relationship between acceleration and velocity. Okay, going on to the next. So our present topic will be the types of graph: position time, velocity time, and acceleration time. So what you can get from position time is your velocity. You can get from the velocity is your acceleration. And the area under the curve of acceleration is your velocity, and the area under the curve of velocity is the displacement. And we will talk about that later. So this is what I told you: the average velocity is the slope of this graph of position versus time. So now let's convert from position to velocity time graph. So here we have different time intervals with different kinds of slopes. So in the first time interval from 0 to 2 seconds, so this one here, so take note that it is having a negative slope. So if you have the final position, -4 minus 0 meters, that was -4 meter divided by 2 seconds, which is 2 minus 0, the time interval. It will give you -2 meter per second. So hence, you draw the slope as a horizontal line in -2 here in the velocity time graph. And here, from 2 to 4 seconds, it's a horizontal, so 0 slope. So 0 here in the velocity. And here in the third, it is having a positive now, so +5 meter per second if you compute the slope of this. Okay, so in other words, Interpreting position versus time graph, the steeper slopes corresponds to faster speeds, and negative slopes correspond to negative velocities, and hence to motion to the left or down. And the slope is a ratio of intervals. Take note, it is just not just 1 point like x over t. No, it's a ratio between intervals, so like delta x over delta t. Okay, so that's for conversion of position to velocity. And here, what if your motion map shows an object that is speeding up? So in the graph, it's a curve now. So it's not having a constant slope because it is already a curve. So what you need to do is to get the tangent line. So another example here. So there are tangent lines in position 1, tangent line in position 2, and in position 3. So take note that when we say tangent line, we have 1 point in the curve and we draw a line that touches that point, okay? And the slope of this will give you the velocity at that point. So like, for example, in this one, position 1, this is a positive slope. This is a zero slope because this is horizontal and this is a negative slope. So if we model it, it's like you throw an object up, positive velocity, and then momentarily it stops before it reverses direction, so negative velocity. Okay, so that's how it is interpreted. Okay, so if we proceed, so there is a question, which position versus time graph represents the motion shown in the diagram below? So here, take note that the object started in the positive x position, then passes through 0 to the negative x position. So in other words, starts with positive, this is already wrong because it starts with 0. Wrong also starts with 0. This one, it's only positive, it doesn't pass to 0, it's wrong. So between D and E. Take note, in E, it starts with negative. Okay, here. This is the positive X here. So therefore, it is letter D, which is the correct answer for this. Okay, so that's the correct answer because in that case, you take note where the object has started. Okay, so the particle starts with positive X and moves to negative X. And then the second question, which velocity versus time graph goes with the position versus time graph on the left? So in this case, it's a combination of a straight and a curved line. So for that straight, it will give you, this is S stands for change position. This is a positive here slope, okay? So it's somewhat like a horizontal line in the velocity. So it's not negative, it's positive. So obviously you can say that it's letter C. So let's see if it's correct. Okay, C. The velocity is the slope of the position graph, and the slope is positive and constant at first until the position graph crosses the axis. So it crosses the axis here. But it doesn't follow that you have to show that it crosses the axis here. Your velocity is the slope of this. So take note, it ends up with like 0. So therefore, the correct answer is letter C, then positive but decreasing because the tangent line here keeps on becoming less steeper. And finally, 0 in the position graph is horizontal. So that's it. Next is discussion. Which position versus time graph goes with the velocity versus time graph on the left? So here, velocity to position, back to position. So take note, velocity is the slope. So meaning if it's a horizontal velocity, positive slope. So it is having a positive slope. So therefore, you can eliminate already this one because it's zero slope. And yeah, these are all positive slope. And here, positive slope also. No, positive slope for this because it's 4, and negative slope for 5 to 10 second, negative 2. So therefore, positive, all positive for this C is wrong. So it's not, cannot be, and also this one. So you're left with this. So this is a positive slope. So if you get the value, final minus initial over the time interval, then also this is negative slope. You get also the value of the position final, which is 0 minus initial 10. You get a negative 2 there. Okay, so that is how to answer that, and the answer is letter B. Okay, so letter B for this. A constant Vx corresponds to linearly increasing x starting from xy is equal to negative 10 meter, xi or initial position. In our case, we can use x naught. Okay, the constant negative Vx and corresponds to a linearly decreasing x. Okay, next, which velocity versus time graph or graphs go with the acceleration versus time graph on the left. So take note, it starts with 0 here, 0 acceleration, so 0 slope. So all of them can qualify. And this one, it's also a negative acceleration, so a negative slope. So ABC will qualify also. But take note, it's initially moving to the right, so it must have a constant. It must have a positive velocity initially. So it eliminates this, and also it eliminates this one because there is no negative slope. It will give you zero, everything zero slope. Okay, and also zero. So here it is eliminated because it is at the negative velocity, meaning it is not started at the right. So you're left with this. Okay, and the correct answer for this is really letter A and B. The velocity is constant while acceleration is zero, and it decreases linearly while A is negative. And graphs A, B, and C all have the same acceleration, but only graphs A and B have a positive initial velocity. So this one. And that represents a particle moving to the right. So this is the velocity time graph. Okay, after the position time graph. So take note that if you have the equation here, v naught plus 80 from the definition of acceleration, which is v minus v naught over time. So take note, if you represent it in a graph, your v naught could be here, the y-intercept, this one, the v naught here. And the A is the slope, the acceleration. So that's why we put A here. So that's why V naught, the y-intercept plus 80. So the 80 is this side, okay, this portion here after the V naught. Okay, that's why it's valid equation if you graph it. So motion in positive direction. Motion in positive direction slowing down also, the slope will become negative. So instead of plus 80, it will become V equals V naught minus 80. Okay, it will become minus 80. Okay, because in this case, this is already in negative slope. And here, motion in negative direction is speeding up. So slope is negative A and starts with negative V naught also. So everything will have a negative sign. Okay, so if it's speeding up. And here changing in direction, so take note from positive velocity to zero velocity because this is the turning point perhaps that it momentarily stops and this negative velocity. So you will have negative V equals V naught, which starts with a positive V naught, then minus AT2. So this is the slope negative A. So that is how to relate with the equations that we have for constant acceleration to the graph. And some examples. So velocity from position, finding velocity from position graphically. So we have this kind of problem in later on in our assessments. So at which labeled point or points does the elevator have the least velocity? So obviously, least velocity is the one with tangent line that gives you horizontal. Okay, this one. So it's C and A. Okay. Then at which point or points does the elevator have maximum velocity? So maximum velocity is having a maximum slope. So if you get this, it's a straight line here, and it's the maximum, so it's letter B. And then sketch an approximate velocity versus time graph for the elevator. So if you sketch that graph of velocity time, so it starts with here, negative. Yeah, this is negative velocity here because it's negative slope, then zero, then positive velocity, maximum, then it keeps on decreasing until zero. So therefore, the correct answer for that will be shown here. Okay, so here. Okay, so in this case, you plot it in terms of the slope. So you start with a positive slope. Okay, so you note this is a positive slope. So there. No, negative slope. I'm sorry. So this is a negative slope because it is like that, ang tangent line. So it's negative slopes, that's why it's negative value. And then at point A, it's zero. So here, zero value of the velocity. And here, it's positive slope. So positive slope here, so all throughout positive until maximum B. So this is a maximum slope. So when we say slope here, we say the value here in velocity. And here, it keeps on decreasing ang tangent line in terms of steepness until zero. So therefore, you plot the values in decreasing until you reach a zero here. So letter C will be here, zero. Okay, so that is how the velocity time graph can be taken from position time graph. Okay, And next, okay, so like for example, this one, just to give you this, a basketball player starts at the left end of the court and moves to the velocity shown. So this one, draw a motion diagram and acceleration versus time graph for the basketball player. So this is the velocity shown here. So if you want to reverse it, you want to have the motion diagram. So since it is having a constant slope, so it's having a constant separation distance. So from 0 to 6 seconds. So here, okay, 0 to 6 seconds. So it's having a velocity. You are going to have it in terms of motion diagram. So it's a bit difficult because in here, you need to have it in position. So since it is a positive slope here, it gives you acceleration, but you have to analyze it in terms of the position of this. So take note that the values of velocity keeps on increasing. So therefore, the position is not a straight line. Because if your position is like this, your position time graph is like this, your velocity time graph will be a horizontal line. But since it is a diagonal line, meaning it's kind of a curve. Okay, so it's kind of a curve that keeps on increasing. So therefore, it could be like this. So nagka-steeper ang slope. So kini nga tangent line until steeper kay until maximum value. So therefore, ang separation distance keeps on increasing until 6. So 0, 1, 2, 3, 4. Okay, 0, 1, 2, 3, 4, 5, 6. So the 6 seconds is here. And then here it slows down also. So meaning the separation distances also will be decreased. So here, take note, okay, it has decreased for the next point until you have here 0 at 9 seconds. So at 9 seconds, when you say 0, there is no separation distance. Okay, and then from 9 to 12 seconds, so it keeps on increasing also in the negative direction because the value is also increasing negatively. So you can have that way. Okay, so and take note, the difference here between this velocity vector will give you the acceleration. That's why you have the acceleration there. Okay, constant acceleration in the orange. Okay. So the most important is you can relate from the velocity to the motion map. So if we plot, okay, if you plot the acceleration, which is the next question, so this is this is having a constant slope. So constant ni siya horizontal. So this is positive. So there, positive 1. So you know how to get the slope of this. And here it's negative. So here, negative slope. So this is the velocity time graph. Oh, the acceleration time graph from velocity. And the velocity to the motion diagram. Okay. And next is the area under the curve. For the area under the curve, like the velocity time graph here, the area of that will give you the displacement. Why? Because if you notice, it forms a triangle because it's under the curve. So here we have the area here of a triangle is 1/2 base times height, and our base there is the time. So we can have 1/2 the time times the velocity. So take note that the velocity from the definition of velocity in terms of the definition of acceleration is v naught plus at. And our at is there, but our v naught is 0 because it starts with 0 here. So therefore, we can substitute v here with 80. So if we change that to 80, it will give you as 1/2 80 squared. Okay, so and take note, this is part of the equation that we have derived already. So 1/2 80 squared. So we have the x minus x naught, if you have noticed, is equal now to v naught t plus 1/2 80 squared. If you can remember, of uniform or constant acceleration. Here in this case, this is the displacement, right? Okay, and V naught is 0, so it will become 0 here, and you are left with 1/2 80 squared, which is actually the area of a triangle, which is under the curve. So the area of a triangle will just give you the equation for the displacement. So that's why it's displacement. And what if your V naught is not zero? It's non-zero here in this graph. So if it's non-zero, take note that there is another area here, a portion, which is the area of a rectangle, to be added to the area of a triangle. So the area of a rectangle is just the time, okay, because it's base times height, times the V naught. So it's V naught times time. And have you noticed that it's V naught times time also here? So therefore, in this second figure, it will just give you x minus x naught is equal now to V naught t plus 1 half at squared, because your V naught is not zero. So it's kind of complete here. It will give you this x minus x naught, which is the displacement, because there's a V naught t here and there is a 1 half at squared here. So that's how to interpret the area under the curve of a velocity to give you the position. And also, the area under the curve of acceleration will give you the velocity there, or the change in velocity. Okay, so that's for our area under the curve. And here, the last one is, I have here the PhET simulation. You just play along with the PhET simulation, because I'll be giving an assignment on this, on how to create a certain graph by adjusting the position, the velocity, and the acceleration. So you can adjust the position. You can adjust the position, the values here, where to put the man. It's negative 10 meter or 0 or 10, and then you adjust the velocity. And if you change the velocity in some time, it will be adjusted also in the position time graph. And also you can put acceleration if you wish, like positive acceleration, negative acceleration. So you can play around in order to get a certain shape of a graph. Okay, so I posted this link. Okay, thank you so much. And that's it for the motion graph. So good luck for this week's activities. If you have questions, so just send me a message through our K-Hub site. Thank you, everyone.